So in this video, we're going to be talking about crystal field theory, and we're going to be doing that before later on in this chapter we talk about the full-blown molecular orbital theory analysis of transition metal complexes, which is more accurate. And so CFT makes some approximations, which we will talk about right now, okay? And the main assumption and approximation is that this is purely an electrostatic model. And so you guys know what electrostatics just means thinking about point charges, right? So if you have two negatively charged points, those are going to repel each other, right? And if you have a negative and a positive point, those are going to attract each other. And so obviously atoms are not points. And so this is the big assumption. The other thing is we're only thinking about this charge relationship. There's other relationships that happen, right? And so that's another thing where this model is an approximation. All right, so the starting point here is that you have some metal ion, transition metal ion, and it is surrounded by a spherical ligand sphere. So what does that mean? That means that you're assuming in the starting point, this is the starting point, that whatever ligands you have, it doesn't even matter at this point how many ligands you have, but let's say for the sake of argument that you have 6 ligands. So that would make it seem like maybe you're octahedral, but you're not octahedral at this point in this thought experiment, okay? You are spherical. So those 6 ligands are moving around somehow. Obviously this can't happen. This is a thought experiment. They're moving around such that they are in a sphere, okay, a perfect sphere, all 6 of them. And what that does, right, is when you just have a metal ion by itself, you have 5 d orbitals, right? We have and we're going to need to become masters of our d orbital shapes. So we'll be going over that through this chapter. You guys got to know that, okay? You know, that's one of the take-home things. You got to know your d orbitals, how they relate to one another. You know, take-home thing past this course, right? So we have the xy, the xz, the yz, x squared minus y squared, and z squared. These are different names for the different functions that make up the electron density for these 5 d orbitals. And the 5 d orbitals for an ion by itself, this is now no ligand. You can think of it like a gas phase ion. The energies of these 5 d orbitals are completely the same. They're quintuply degenerate, right? All 5 are the same. Now what we're going to do is we're doing this hypothetical spherical ligand sphere. Let's say there's 6 ligands, they're moving around hypothetically just so that they make a sphere. What is going to happen? And thinking about this purely in an electrostatic sense, there are electron clouds, right, on the ligands, and there's electron clouds on the metal ion. And we're just thinking about electrostatics here. We're not actually thinking about bonding. Okay, that's what we're missing out on. And we'll do that when we get to molecular orbital theory. But we're just thinking about the negative charge on the electron cloud around all these ligands and the negative charge on the electron cloud of the metal ions. So you have negative electrons in these electron clouds, like in the orbitals, right? And so that is going to cause all these energies to go up, right? Because you have electron-electron repulsions. So the negative charge of ligands, just the fact that there's electrons in there, causes all these orbitals to go up. Now, they're still going to be degenerate at this point. What we're going to do next in our thought experiment is now we're going to say, hey, okay, we're at this point. What happens is the sphere stops being a sphere, and now these ligands hold their places in an octahedral environment. Let's say we started with 6 ligands. What's going to happen then? Okay, and so in order to do that, we have to think about how these functions, right, xy, xz, yz, x squared minus yz, and z squared, what is the symmetry of those in octahedral space? How do they transform? In spherical symmetry, which, by the way, we don't have a character table for spherical symmetry. What is the point group of a sphere? there is a point group. It's called R3, but there's no molecule that's a sphere. Point group of an atom is R3, but we don't use the R3 character table. Okay, R3 just stands for real dimension 3. So there's 3 dimensions. Okay, it's the most symmetric thing you can have in 3 dimensions is R3, and it's a sphere. But anyway, so in spherical symmetry, right, all 5 d orbitals are degenerate. What happens in octahedral symmetry? Well, we can look at the functions of the d orbitals, and those are right here. Here you can see xz, yz, and xy. Those quadratic functions have the same symmetry as the dxz, the dyz, and the dxy orbitals. So that's telling you that in octahedral symmetry, these 3 orbitals, dxz, dyz, and dxy, transform together. They're triply degenerate, and they have the symmetry T2G, okay? Now we have the x squared minus y squared orbital and function, and we have this function here, 2z squared minus x squared minus y squared. Now, this is something you may not have ever learned before. If you've gone over just basic general chemistry d orbitals, you know, we call the d orbital dz squared. That z squared is actually an abbreviation, okay? The real function that you mean when you say dz squared, you mean d2z squared minus x squared minus y squared. But nobody likes saying that because it's too long. But that's the real function. That's the function that gets things to be orthogonal, orthonormal, all that stuff, right? And so that is the true function. So if you see this 2z squared minus x squared minus y squared on a character table, that means dz squared, okay? Or that's the function that corresponds to dz squared, has the same symmetry. So the dz squared orbital and the dx squared minus y squared orbital transform together in octahedral symmetry, in OH symmetry, and they have the symmetry of EG, okay? Now here, z squared is shorthand for 2z squared minus x squared minus y squared. So this is essentially the way to think about this, is that once the ligands approach the metal in an octahedral environment, they are going to split. The dz squared and the x squared minus y squared are going to have one symmetry and one energy. It's going to be Eg. And the remaining orbitals, the xy, the yz, and the xz, transform together. They're triply degenerate, and they transform as T2G. Now, they're going to have different energies. Why is that? And why are the T2Gs lower in energy and the EGs, you know, according to this diagram I showed you, higher in energy? Here's why. We're only thinking about electrostatics here. And so let's start with the EGs. The EGs, this is the shape of the dz squared, right? There's a donut in the center and sort of this P-like lobe. If you look at the orientation of that, and then look at where your octahedral symmetry ligands will be, you have direct interaction between this lobe and this ligand, this axial ligand we call it, and this lobe and this ligand. And remember, we're saying that any interaction right now is repulsive because it's electron-electron interaction between the 2 electron clouds. And so these direct interactions there are highly unfavorable, right? Similarly, take a look at dx squared minus y squared. It's directly interacting. These 4 lobes are directly interacting with these 4 ligands, equatorial ligands. So these are relatively high energy. Now it turns out the overall energy is the same, and we'll talk about why. You know, you might be thinking, well, there's 2 lobes here, 4 lobes here. Why? Well, there's also the donut here, and the amount of interaction of each of these lobes in each case is different. And we'll be able to actually quantify this later on in this chapter. But for now, I just qualitatively want you to see that, yeah, you have for the EG lobes that are directly pointing the ligands, and that causes the EG to be high in energy. Contrast that with the T2G. Look at the orientation of the XY, the YZ, and the XZ. In all of these cases, your lobes are pointing in between ligands. It's not directly on the axis of the ligand, okay? And so because of that, these are lower in energy, of less electron-electron repulsion. And you can kind of see how all 3 of these would be triply degenerate It's easier to see that qualitatively than this case where you have the donut to consider. Because these are just different orientations of orbitals. They're the same fundamental shape, and they're just oriented in different axes. They're equally pointing in between ligands in all three cases. So we can go back here and finalize our picture where we started out with the metal ion. We increase the energy when we have a spherical ligand sphere due to electron-electron repulsion, but everything stays quintuply degenerate. And then we impose an octahedral ligand set, and that's where we get this splitting into the doubly degenerate higher lying 2 EG orbitals and the triply degenerate lower lying 3 T2G orbitals. Okay, and so we can think about the energetics here because we have 2 orbitals that move up in energy and 3 orbitals that move down in energy, and the overall energy can't change. The overall average energy has to be right here where we started, right in the center. That means that these 2 EG orbitals had to go up 0.6 in energy, 0.6 times some arbitrary unit, and minus 0.4, the T2Gs had to go down, right? And so we call the gap between the EG and the T2G delta O, okay? And so the average has to stay the same, and that's what this is saying. 2 times plus 0.6 times delta O plus 3 times minus 0.4 times delta O equals 0. Because we have 3 that went down, minus 0.4, and 2 that went up 0.6, that's 0. So our barycenter or average orbital energy is the same here. dQ is another unit that is used, and people call it 10 dQ, okay? Why? They're trying to make it easier so you don't have these points. So now you talk about 6 and 4, okay? You'd say that these went up 6 dQ and the T2Gs went down 4 dQ. So 10 dQ is the same thing as delta O. So if you ever see that, you know, just know that it's just a conversion. There's just different nomenclatures. All right, so that's sort of, you know, the meat of crystal field theory, and we'll see how we can apply this to various transition metal complexes in the next video.